Hello everyone, welcome to the Load Flow Analysis Practical of Power Systems 1 module. So let's get started with an introduction on the theory parts that are needed in order to understand the practical. Objectives of this practical are to familiarize with the major components of a typical power system and universally accepted symbols used to identify such components, to understand why and how complex three-phase systems are represented by single line diagrams, to observe and discuss the operation of power systems with varying configurations by interpreting the measurements made at different locations in the power system. In this practical, we will be using the University of Moratuwa real-life power system simulator at the Power Systems Lab. First, let us learn what a power system simulator is. It's a model that has been built up using actual electrical components such as synchronous generator, transformer, transmission line models, and vacuum circuit breaker panels with electromechanical and numerical protection relays. This voltage scaled down version of the actual system is expected to fulfill the requirement, providing a practical exposure to the students. An actual power system has many different components connected together. For power system modeling, we can identify the following main components used. They are the synchronous generator, substation, transmission lines and line models, loads and load models. Then we can use power flow analysis techniques for planning and operation of the power system. Now let us learn a bit more in depth about these areas separately. First, let us learn about synchronous generators. Large-scale power is generated by three-phase synchronous generators driven by steam turbines, hydro turbines, or gas turbines. Depending on the construction of the rotor, synchronous generators can be divided into two as cylindrical rotor generators and salient pole rotor generators. Cylindrical rotor generators have a relatively large axial length and small diameter to limit the centrifugal forces. And these are mainly driven by high-speed prime movers such as steam turbines and gas turbines. Salient pole rotor generators, on the other hand, have a short axial length and a large diameter, and they are driven by low-speed prime movers such as hydro turbines. Though in actual power systems, turbines are used as prime movers, for generators in our power system simulator model, we are using an induction motor as the prime mover. To control the speed of the motor, variable speed drive is used. We also need to have an excitation method for the generator. Generator excitation means supplying DC current to the field DC winding. Generally, we can use separate excitation, brushless excitation, or shaft-end DC generator type excitation. Next part of a power system is the substation. It is part of an electrical generation, transmission and distribution system which transform voltage from high to low or the reverse depending on the transmission and distribution. In a transmission substation, voltage will be stepped up to avoid the losses during the transmission. In a distribution substation, voltage will be stepped down. Apart from step-up and step-down transformers, various equipment for safety purposes are established in the substation such as circuit breakers, isolators, current transformers, voltage transformers, and surge arresters. In this practical, the generating voltage will be stepped down using a step-down transformer for safety purposes. During the practical, step-up and step-down transformers will provide the purpose of the substation. The safety equipment used in a substation are not used in the power system simulator model. Next part of a power system modeling is transmission lines and line models. The purpose of having transmission lines is to transfer electric energy from generating units to the distribution system. The electrical behavior of a transmission line under normal operating conditions is characterized by four electrical parameters, namely line resistance, line inductance, line conductance, and line capacitance. Transmission lines can be studied under the three models, namely short line model, medium line model, and long line model. Transmission lines can be represented as a two-port network, and for practical reasons, we are using the phi network over the T network for transmission line models. Short line model is used for transmission lines with length less than 80 kilometers, where the capacitance can be ignored without much error. This model can be represented as shown in this diagram. Medium line models are for transmission lines with the length in between 80 to 250 kilometers. Due to the higher length, the line charging current becomes larger. So the shunt capacitance is now considered and the normal pi model is built as shown in the diagram. Lines of length 250 kilometers and longer are considered as long lines. When modeling a long line model for more accurate solutions, the exact effect of the distributed parameters must be considered as shown in the diagram. Loads of power system can be divided into mainly three categories, which are industrial, commercial, and residential. Industrial loads accounts to composite loads and induction motors, which are functions of voltage and frequency and performs a major part of the system load. Commercial and residential loads consist of lighting, heating, and cooling. These loads are independent of frequency and consume a negligible amount of reactive power. Load models can be categorized into static load models and dynamic load models. In static models, active and reactive power at any instant of time is represented as functions of bus voltage magnitudes and frequency, while in dynamic load models, the active and reactive powers are expressed as function of voltage and time. One of the most important parts of power system modeling is power flow analysis. It is also referred as load flow analysis, which is the backbone of power system analysis and design and is necessary for planning, operation, economic scheduling, and exchange of power between utilities. In power flow analysis, we determine the magnitude and phase angle of voltages at each bus and active and reactive power in each line. The most commonly used methods to obtain power flow solutions are Gauss-Seidel method, Newton-Raphson method, and fast decoupled method. Now that we have an idea of what power system modeling is, let us move on to the practical. Before starting the practical, first look at the single line diagram provided to you and try to identify the components and collect the nameplate details. Next, let us look at how the components are connected to each other. First, you will see the main panel with the main circuit breaker and the circuit breaker relevant to the generator. Then it is connected to the circuit breaker and the power supply switch for the variable speed drive. Then it is connected to the generator and the prime mover, which is an induction motor in this practical. For the DC excitation of the generator, we will be building a separate excitation circuit which consists of two 12-volt batteries, a rheostat, and a circuit breaker. Then the generator is connected to the transformer 1 through a circuit breaker. How the circuit breaker panel looks like and the nameplate data can be seen as follows. The transformer 1 is a step-down transformer in this practical. It is then connected to another circuit breaker and then to the bus bar. Then another circuit breaker can be seen before the connection to the transmission lines. After the transmission line, the circuit is continued to another bus bar through a circuit breaker. Then, after another circuit breaker, you could find the distribution transformer. After the distribution transformer, we can find the load, which is a resistive load in this practical. Now that you have a clear idea of how the circuit is built, let us move on to the procedure. First, switch on the circuit breaker of the excitation circuit and put the multimeter to its DC voltage range. Then measure the voltage at the field terminals of the generator. Change the rheostat until the voltage becomes 18.02 volts and then turn the circuit breaker of the excitation circuit off. Then identify the three auxiliary supply circuit breakers. The first circuit breaker is for the 230 volt AC supply used for the spring charging motors. The second circuit breaker is the 220 volt DC supply for relays. The third circuit breaker is the 24 volts DC supply for the indicator lights. For the 220 volts DC supply, we have to turn on the DC generator. For the 24 volts DC, we will be using a DC power supply. You will see the indicator lights turning on when the circuit breaker is turned on. Next, turn on the main circuit breaker and the circuit breaker relevant to the generator. Then, turn on the circuit breaker and the power supply for the variable speed drive. When you turn on the variable speed drive, you will see the induction motor starting. Then turn on the breaker of the excitation circuit. Next, we have to turn on the circuit breaker number 1 to energize the transformer 1. When turning on the circuit breaker, there are two methods which can be used. They are the manual charging and the spring charging. In manual charging, first we must turn the manual circuit breaker operating knob to on position. Then you will see the on-off indicator and the indicator lights become red. Then, using a T-rod, we can manually charge until the charged position becomes red. You will also be able to hear a sound when the circuit breaker is fully charged. Now, let us look how it is done. The next charging method is the spring charging. Here, when we change the manual circuit breaker operating knob to on position, the spring charging option will automatically charge and make the charged position red. We can hear the sound of the charging when using the spring charging. Now let us see how it is done in the practical. Then measure the transformer 1 primary line-to-line voltage. Next, measure the transformer 1 secondary line-to-line voltage. Then turn on the circuit breaker 2 to energize the bus bars and circuit breaker 6 to energize the transmission line 1. Then measure the line-to-line voltage at the sending end of the transmission line. Next, measure the line-to-line voltage at the receiving end of the transmission line. Then turn on the circuit breaker 11 to energize the bus bars and the circuit breaker 16 to energize the distribution transformer. Measure the primary line-to-line voltage of the distribution transformer. Then measure the secondary line-to-line voltage of the distribution transformer. The following calculations should be done. As for the discussion, you should answer the following questions in your coursework. With that, we have come to the end of our practical. Hope you enjoyed learning about load flow analysis. Have a great day. Thank you.